good time?
Let's do this.
I see Dave Lyons over there. I don't know if he's coming in here.
Okay.
Yeah. All right, sweetie pie.
Good evening, everyone. Welcome to Science on Tap. I'm Rin Herman. I'm the Creative District Curator, and I want to start this evening with a little joke. Why did the physics professor and the biology professor break up? There was no chemistry! Thank you very much. I'll be here all week.
Tip your server.
All right. So, the On Tap program is put together by the Creative District, and I'm delighted to introduce Linda Deck, who will let you know all about tonight's program. Let's put it up for Linda Deck.
Wow, Rin Herman. Thank you, Rin. That was very nice of you. Rin just recently took on the role as curator of the Creative District, and we're really happy to have her there. She's a real go-getter. So keep your eyes open for other events going on in the Creative District. One of the big ones that's coming up in October will be the Night of Arts and Culture on October 13th. It's going to be sort of an arts and culture walk of around 9-10 different venues right down here.
All right downtown.
Walkable Creative District. There's going to be performances. There's going to be
Music, performing arts.
all sorts of good stuff. So please come to that. That should be a lot of fun. That's Friday the 13th of October. Yeah. So I've just mentioned the Creative District. Before I go any further, I want to say that today's On Tap is sponsored by the American Chemical Society, Central New Mexico Local Center. Yay! Thank you for the great eats, and thank you very much, Ning, and your entourage for getting all the eats here and making it so nice. So thank you very much. Do you want to say a few words?
Sure. My name is Ming Xi. I'm the chair-elect of the local ACX section. We're called Central New Mexico Local Section. And if you, we have activities, we have all kinds of things. If you want to know more about it, please let me know. I don't know the best way. I say, let me know what that means. So you can just ask Linda, and then she will, relay all the information. And if you want to join ACS, by no means, like me and Donovan know, we're going to be here after this for a little while. So thank you, and thanks all our ACS members for coming in.
Yes. So that's the best way. They will linger after On Tap. So buttonhole them and talk with them about this great society. Wonderful. Another thank you so much, as always, to Uncorked for hosting us. Always fantastic. Great venue. We appreciate it. I see a lot of you have patronized the bar already. Excellent. Don't be shy. Keep it up. So the next Science on Tap, before we even get to this one, the next Science on Tap will be the third Thursday of October. It's always the third Thursday. That will be the 19th. And our presenter will be Ross McDonald, a scientist at the Pulsed Field Facility of the National High Magnetics Field Laboratory here at Los Alamos National Laboratory. I'm sure he's going to be talking about something interesting. They're always doing new, neat things out there. So here's how On Tap works. If you've never been before, and actually I see a lot of our wonderful regulars here. Thank you for coming back. For all the newbies, here's how it works. This is a discussion whereby we're learning from scientists at Los Alamos National Laboratory about the latest cool research that's going on there. So they will give, and tonight it's Sharon. Sharon will give about a 15-minute preamble about what it is that she does and some of the cool stuff that's going on, and kind of prime you for questions. And then it's really up to you. Start asking questions. We want to get this as more of a conversation among us all to explore these topics. So don't be shy. Get right in there. And it's your opportunity to ask those questions that you were wondering about. So she'll be great at it. I'm absolutely certain. We've become a really nice family here at Science on Tap. It's been going on for almost almost 4 years now. Pretty amazing. And I'm sorry to have to report the passing of one of us, and I feel this deeply. Glenn Graves passed away just last week. While at the laboratory, Glenn worked on the rover program and the possibility of nuclear-based rocketry. He later did stints as the head of the physics section of the IAEA in Vienna. He was at NSF as acting director of the Office of Energy Research and Development Policy, and he was a science advisor in the administrations to the president in the Carter and Ford administration. So quite an accomplished fellow. Here, he was always very interested and participated in our thoughtful Science on Tap exploration of topics. So we're going to miss Glenn deeply. Tell you right now, please turn off your cell phones or quiet them. And there are comment forms on your tables. Please let us know how we did tonight, if we could have done anything better, and especially give us ideas for subsequent speakers. We really like to bring in the people that you're interested to hear from.
Real quick, the reason
Yes,
we're having
ma'am.
the Magnet Lab people here next month is because of comments on the feedback form. So we do listen.
My partner in crime, another Linda Anderman. So thank you, Linda, for saying that. That's why we're having that speaker. All right, so let me introduce tonight's speaker. Sharon Bone is currently a postdoctoral researcher at LANL in the Inorganic Isotope and Actinide Chemistry group, where she does research on issues concerning medical isotopes and nuclear waste management. She's been at the laboratory all of 5 months. Yay! Yay! Sharon received a bachelor's degree in chemistry from Vassar, a master's degree in civil and environmental engineering from UC Berkeley, and then a PhD in environmental science, policy, and management also from UC Berkeley. She's been working on problems associated with environmental contamination since she was an undergrad in such diverse environments as upstate New York, the waters off of Cape Cod, San Francisco Bay, and the Colorado River Basin. So Sharon now is going to talk with us about work doing here at LANL. So welcome, please, Sharon Bone.
Thank you. Okay, so I'm going to start by throwing out kind of a long sentence to you, so just bear with me. I'm going to tell you about how naturally occurring biogeochemical processes can help to limit the extent of environmental contamination. So let me start unpacking that by describing to you what biogeochemistry is. It's a scientific discipline. I'm a biogeochemist. And what I do is I try to understand how biological processes couple to geochemical processes to control the movement of atoms or particular elements through the environment. So I'm going to give you a couple examples of what I mean by biological and geochemical processes, but what I want you to focus on is this idea that we're tracking how an element moves through the environment. So for instance, if I'm interested in carbon biogeochemistry, I might be interested in how carbon atoms move from a fossil fuel into the atmosphere, into a plant, into the soil. By tracking how those atoms move, I gain insight into larger phenomena like climate change. So as a researcher, I've actually been interested in the biogeochemical cycles of elements that are toxic metals, things like uranium, lead, and mercury. And I'm interested in these metals because, of course, they pose a hazard to human health, to wildlife, and they contribute to environmental or ecosystem degradation. I'm also interested in these toxic metals because they're largely mobilized in the environment as a result of human activity. So things like use in consumer products, industrial.
Can you speak up just a little?
Oh, sorry.
Is the microphone available? Is it on? Oh, okay. Do you want to use the microphone? Or just use your teacher voice?
Let me see if I can adjust my voice quickly, because I'm not like a good deep speaker, but we'll try. Okay. Toxic metals, they're mobilized in the environment in consumer products, industrial practices, energy production, and of course the mining that goes into supporting all of that. And once this contamination is released into the environment, it can be very costly and difficult to remove. Sometimes we can actually go in and clean up an environment by removing the contaminated material, but often that's not possible. So what we focus on instead is converting that toxic metal from a form that is available to be taken up by organisms to a form that's less available to those organisms. That is termed bioavailability. And the idea is that if something is not bioavailable, it can't get into the organism and it can't induce a toxic response in the first place. So bioavailability depends upon the form that element is in. And we can actually think about form in 3 tiers. So the broadest tier that we think about is simply where that element is located in the environment. Do you find it in water? Do you find it in soil, groundwater, a lake, etc.? The second tier down is whether that element is occurring in as dissolved in water. Is it in the aqueous phase, or is it in a mineral? Is it in the solid phase? The third tier down below that is the actual chemical form of the element. So different elements have different numbers of electrons surrounding the nucleus. That's called an oxidation state. And most elements have at least a couple of different oxidation states that they can exist in. The other part of chemical form is the number and type of other atoms that element is bound to, and that's called its coordination environment. So I think you can see how both the oxidation state and the coordination environment are going to determine whether this element ends up in dissolved in water or it ends up in a solid, and that's going to really determine how it's distributed in the environment, in waters or soils. So as a scientist, I actually use a suite of tools that allow me to access all of these different tiers of forms. So I use tools which allow me to look at the landscape scale, and I use tools that allow me to look at the molecular scale, so to actually determine the chemical form of that toxic metal and how it's distributed in the environment. So I'm going to give you just 2 examples of how a toxic metal can be transformed into a less bioavailable form by naturally occurring materials or biological processes. So I'll give you 2 examples. I'll start with mercury, and then I'll go on to talk about uranium. So mercury is toxic, and it's really toxic. It's toxic to everybody across the tree of life, from people down to bacteria. Nobody likes it. Also, currently, the dominant source of mercury to the environment is burning of fossil fuels. So it occurs as a trace contaminant in fuels. When they're combusted, it goes up into the atmosphere, and then the atmosphere is really good at transporting mercury globally. So mercury contamination is really a global problem. Okay, so a key step in mercury's biogeochemical cycle is its conversion from a dissolved mercury salt by a particular set of bacteria that happen to live in oxygen-free environments. So when I say oxygen-free environments, think about sediment that's beneath an estuary, sediment that's beneath a lake, where the supply of oxygen is limited. So these bacteria that live in these environments, they take the dissolved mercury salt and they convert it into a compound that's called methylmercury. Methylmercury is really bad, and it's really bad for a couple of reasons. First, it's many more times toxic than other forms of mercury. If you took a concentrated solution of this methylmercury and you dropped it on your hand, it would go through your skin and into your bloodstream, and it would kill you. It's really dangerous. The other problem with methylmercury is that it is magnified as you go up the food chain. So as you start down at the bottom of a food chain with like a small invertebrate, the mercury concentration can be, a trillionth of a gram per gram of that, if you took a gram of those organisms or something. By the time you get up to the top of the food chain, to like tuna fish and swordfish, you have mercury or methylmercury concentrations that are about a microgram in maybe a gram of that fish. And so those concentrations, they're not lethal, but they're still hazardous. And it's actually the dominant exposure pathway of people to mercury in the environment just generally. So this process of conversion to methylmercury is not something we like. So in my research, what I've done is I've tried to figure out whether there are any naturally occurring materials that are present in these low oxygen environments, like these estuary or lake sediments, that can take mercury and put it into a form that the bacteria can't convert to methylmercury. So I ended up looking at a mineral. This mineral is called McKenowite. It's named after the Mackinac mine in Washington State. I don't know why. And it's composed of iron and sulfide. Now, I chose to focus on this mineral because, firstly, it's just really common in these sediments, and secondly, it has chemical processes, or chemical characteristics that I thought would be conducive to reacting with mercury. So I took some of this dissolved mercury salt and I mixed it with the mineral McKenowite, and I used some tools to follow how the form of mercury was changing during that interaction. And what I found was that the dissolved salt was actually converted into metallic mercury. And this is really great because metallic mercury is not used by these bacteria to form methyl mercury. The metallic mercury has to be turned back into the dissolved salt before it can form this dangerous compound. So basically, this mineral was transforming mercury into a form that was not bioavailable to these bacteria, and so it's limiting the toxic impact of mercury contamination. What's also really nice is that the researchers didn't know that there were processes that could generate metallic mercury in these sorts of sediments. So our research showed that metallic mercury could actually be a pretty important constituent there. Okay, so I hope that example just demonstrated for you that minerals can be really important. Reactive phases, they can limit the bioavailability of these toxic metals. The second example that I have for you tonight is uranium. And in part, I'd like to talk about uranium because it's a groundwater contaminant in a lot of western states, in particular in Wyoming and Colorado and New Mexico. Not all groundwater, but there are particular groundwater sites. And this is because there's been a lot of uranium mining in the western US. Now, when ore is extracted from those mines, the uranium has to be extracted, out of the ore. And during that process, you get a little bit of uranium and you get a lot of waste rock. So these facilities, or these industrial plants that are doing this uranium extraction process, they're left over with piles and piles of this stuff. So what do? They just put it in a pile outside and left it on the ground, of course. So then in the 1970s, we realized that this was a pretty hazardous way to deal with this waste rock, and Congress passed a law saying that we had to remove it and put it in a proper waste facility. But, and that was done, that's great. But while that rock was sitting out there on the ground, the uranium that was left over in that rock that hadn't been taken out during the extraction process leached out of the rock and accumulated in the groundwater below. So currently, the Department of Energy, specifically the Office of Legacy Management, has a number of sites throughout Colorado, Wyoming, and New Mexico primarily, where they have to manage the uranium concentration in this groundwater. And this is a pretty thorny task for them, and that's because these uranium concentrations are hazardous, but they're also very low. So the EPA regulatory limit for uranium in water is 30 parts per billion. So think about that. That's pretty challenging to get uranium concentrations down below 30 parts per billion using some sort of technology. Luckily, researchers have actually known for a long time that there are bacteria that exist underground where this groundwater is located that can take uranium from the groundwater, and they can change the form of uranium to one that, instead of being in the aqueous phase, accumulates in the solid phase as well and goes into the sediment. So that's great. You're taking uranium out of the groundwater where it could be available to people if you pull up that groundwater and try to drink it, and you're putting it in a form that's not going to move. So there's actually been a really long effort by researchers to feed these organisms in the ground so that they do this process for it. So people were actually injecting vinegar into the ground, acetate, in order to stimulate these bacteria. So the bacteria eat up the vinegar, they think it's really good, they like it a lot, they grow, and they convert uranium into a form that exists in the sediments. But the problem was, if you don't keep feeding them the vinegar, then they die and they stop doing this process. So in my research, I was interested in understanding whether there were organic food sources in the ground that could fuel this process, this bacterial process. And what we found was that that was in fact the case. These sites exhibit hotspots that are enriched in organics, and these organics are derived from plant material that gets buried and it slowly decomposes underground, and it acts as a really good bacteria food source. So the bacteria take that uranium, they turn it into sedimentary uranium, and everything is good. We wanted to see how robust this process was. So we looked at the chemical form of uranium that was in these organic hotspots, and we actually found that uranium was directly complexing to that organic material. This was a little surprising to us. We thought that what was going to happen was that uranium in the sediments was going to form a mineral. We thought it was going to form a uranium oxide mineral. And that mineral is really stable, and it's not very susceptible to change